Hi, and welcome to a new lecture of mechanics in which we will learn about some relationships that exist between the distributed load, shear force, and bending moment in a beam. It's very useful to establish if we can have these relationships because they might be tremendously helpful in drawing the internal force diagrams, the shear force and bending moment diagrams. So let's assume a general case of a beam loaded by some kind of distributed load, the beam being simply supported, as you can see. Here's the distributed load. Has a general shape, so it can be any load really. And what we want to do is we want to establish a relationship between this load and the internal forces in the beam in terms of the shear force and bending moment. So for this purpose, we're going to cut a very small element of the beam, very tiny little infinitesimally small element that has a length dz, a very small length dz. And we will take this element out from the beam, draw it here separately, and actually drawing its free body diagram with all the forces that act on it. And these would be, of course, the external force, the distributed force that acts on the element, on the dz wide element at the top, like so, as well as the internal forces on the two sides of the element, because we've cut the element along two planes. So on the left hand side, positive shear, right hand side, positive shear, and also positive bending moment on the left side and positive bending moment on the right hand side. The values of these internal forces are M and V on the left hand side, and then the same values plus a change on the right hand side. So the shear force will be equal to V plus dV, a change in the shear force, and M will be equal to M plus dM, a change in the bending moment. For equilibrium, we can sum the forces on the vertical direction. So we will get an equation like this one. And from here we can solve for the value of the load, which will be equal to negative dV dz. So a very important relationship which tell us that, in fact, if you remember some of the properties of the derivative, indicates that the slope of the shear force equals to the negative of the distributed load. So if the distributed is positive, if the distributed load is above the beam, that's a positive distributed load, then the slope of the shear force will be negative. Now, one caveat, this is valid only for distributed loads. It's not valid for concentrated forces, which represent discontinuities in the beam, in the loading of the beam. So we can apply these relationships only for distributed forces. Now the second equation of equilibrium would be summing the moments, let's say about point T here at the bottom left corner, equals to 0. So we will have M on the left hand side, M plus dM on the right hand side, minus V plus dV times the moment arm dz, also on the right hand side, plus the moment produced by the distributed load, W dz times the moment arm half dz, minus M on the left hand side equals 0. And obviously the force, shear force V, goes through T, so it's not in this equation. M and M cancel out, and we can write the following simplified equation, in which you'll notice that we have two terms containing two small infinitesimally small elements that are multiplied together, like d something times d something. So that means again we're multiplying something very, very small by something very, very small, and the result would be probably something close to zero. Really can be approximated to zero. So hence we can cancel out these two terms, consider them as being equal to zero, and in the end we can solve for the shear force that will be equal to the derivative of the bending moment. Another important relationship, very important relationship, which will indicate now that the slope of the bending moment in a bending moment diagram equals to the magnitude of the shear force. So it's very important, as if we know these values, the value of the shear force, we know how the bending moment diagram would look like. Now in the end we can express the negative of the distributed force as the derivative of the shear force, and that will be equal to the derivative of the bending moment, or d2m by dz2. Very, very important relationships, and you will see in the future examples we will apply these relationships between the distributed load and shear force and bending moment diagrams, and that's why it's very important to review, to remember some basic properties of the derivatives. So I would suggest, before watching the next lecture, to review these properties, not in depth, but you just need to know some relationships between the function and its derivative, like for example about the slope, the maximum values of a function where the derivative is zero, and so forth. So please do review those properties, and once you have done that, I will see you again at the next lecture. In the meantime, thank you very much for watching this one.